I'm going to do some of these reactions on the testing halogenoalkanes worksheet, and the first one is to have a go at burning a halogenoalkane. Now really I should be doing this in the fume cupboard, and certainly if you were in the lesson with all of you trying to do it, I'd insist you'd be doing it in the fume cupboard, but because it's just me doing just one of them, I think the lab's well ventilated enough, I don't need to worry. I'm going to try burning this, and this isn't terribly convincing, I must admit, as a reaction, because halogenoalkanes typically are used as flame retardants on furniture and can be used in fire extinguishers, so the results of this experiment aren't brilliantly convincing that it's not very combustible. You can see it has ignited. You can see also there's a lot of nasty thick black smoke coming off it as well. Okay, but generally halogenoalkanes, particularly the more and more halogens that they have in the molecule, the less combustible it is. So this was chlorobutane, so actually there's quite a lot of carbon in that for the amount of halogen. You can see that it was a really nasty smoky flame, and some of you may have even noticed some slight tinges of green around the edge of the flame. This is the second experiment on the sheet. So this is looking at the reaction of halogenoalkanes with aqueous alkali. Now, halogenoalkanes aren't soluble in water at all, and you might like to have a think about why that is. So if I were just to use normal sodium hydroxide dissolved in water, it would make the reaction a little bit more difficult, because the halogenoalkane wouldn't be able to come into contact very easily with the hydroxide ions, because they're in completely different phases, completely different solvents, and you'd see it as two separate layers in the boiling tube there. So what I've done is to dissolve my, in fact, potassium hydroxide in some ethanol. Now the ethanol acts as what we call a bridging solvent. So the halogenoalkane is soluble in the ethanol, and the potassium hydroxide is also soluble in the ethanol. So it allows the two species to come into contact with each other. So I've put that into the boiling tube already. I've added a little bit of water, and now I'm about to add some halogenoalkane to the mixture. Okay, so I've got 2-chloro-2-methyl-propane. Add a little bit of that. Need to give it a little bit of time to mix and react. And hopefully you can see there are no layers there in that boiling tube, so that's evidence that my ethanol has allowed the two species to mix. It really has done its job as that bridging solvent. Okay. What I'm going to do now is to use some nitric acid to neutralise any excess hydroxide ions. I'm quite generous with that, because this solution of hydroxide ions in the first place was quite concentrated. And finally, I'm going to add some silver nitrate solution. Now the job of silver nitrate solution is to test for halide ions. So seeing as I had 2-chloro-2-methyl-propane at the start, you might like to guess which colour precipitate you think I'm going to form from the halide ion that's present. Now I hope you guessed correctly that it was going to be a white precipitate, because it's formed silver chloride in there. I think it's very nicely convincing. And you might like to wonder what the halogenoalkane has formed by reacting with the hydroxide ions if that chloride ion has now been displaced. In this experiment, I'm going to effectively mimic exactly what was done in experiment 2. So I'm going to hydrolyse my halogenoalkanes, so effectively turn them from a halogenoalkane to an alcohol, except that this time I'm not going to use any hydroxide ions to do it. I'm just going to rely on the water that will be present in the solution. So it will be a slightly slower reaction, and that's why I've got this water bath ready here in order to help try to sort of speed it up a little bit. It just helps the mechanics of organising this a little bit better. So what I want to do is to compare how quickly this hydrolysis happens on these 3 different halogenoalkanes. So I've got a chlorobutane, a bromobutane and an iodobutane. They're already in these boiling tubes, and I'm about to add some silver nitrate solution to them, and then I'm going to stand them into the water bath. And what we want to do is to compare compare how quickly they form the precipitate, because obviously that will be the indicator of when a hydroxide ion or water, and then it will lose a proton to become OH, will go on to my my butyl stem, and the chloride ion or the bromide ion and the or the iodide ion will be displaced. So depending on which one forms the precipitate first, that will tell me about which one is reacting most quickly and easily. So I'm going to try and add a decent amount of nitric acid to each of them, silver nitrate to each of them in turn, and then stick them pretty quickly into that water bath. And then we can compare which one forms the precipitate first. I think one of them's starting to do it already. I'm just going to lift it out and see if you can see. Okay, I think there's some evidence that one of them is trying to do it already. I'm going to stick them back in again and get more conclusive evidence. Lift them out again and have another look. Okay. I think you can see that the iodide tube has already started to make the precipitate. It's quite watery looking, I suppose, because there's a lot of liquid in there, so it's not a very dense precipitate. But you can also see, I think, starting, just beginning in the bromide tube, that's looking slightly different from the end one, the chlorine one. It's looking like it's got some cloudiness to it as well. So let's pop them back in the water bath and have a look at them again in a moment. Okay, I'm lifting them out now for the final time to have a look at. Okay. So again, the precipitates aren't very dense, but I hope you're convinced that the iodide formed the precipitate first, then the bromide is clearly trying to do that, and the chloride hasn't even started yet. Okay, you might like to have a think about the carbon-halogen bond and features about the carbon-halogen bond, and try to think about why it might be that the carbon-iodine bond broke first, the carbon-bromine bond broke second, and the carbon-chlorine bond is most resistant to breaking. So we'll talk about that later. This is the final experiment on the sheet, so experiment 4, and I'm comparing position isomers this time of chlorobutane. So this is one chlorobutane in this one, and well, it's in a primary position. This is 2 chlorobutanes, so my chlorine is attached in a secondary position, and this is 2-chloro-2-methyl-propane, so my chlorine is attached in what we call a tertiary position. And I want to compare this time the rate of hydrolysis. So I'm going to do the same experiment as I did before, which is to add some silver nitrate to them and then stand them in the water bath. And we'll keep lifting them out and seeing which one forms the precipitate first. So I've already got my samples of the halogenoalkane in the boiling tube. So let's quickly add some some silver nitrate. Well, crikey, that one's even doing it before I've even got it in the water bath. I'll pop them in the water bath and lift them out in a moment and compare them. lift them out. I think that's really convincing. You can see in that end tube there, we're really definitely getting a precipitate forming. So the tertiary position seems to be reacting very quickly. And that's quite interesting because last time, when we were comparing the rates of hydrolysis, the chloroalkane was reacting the slowest, and yet here we've got a chloroalkane that was reacting pretty quickly. So let's see which one comes next. It's been quite a long period of time now, a good 5 minutes, between that first one starting to do anything and the others starting to do anything. So I'm just lifting them out now so that you can compare. And you can see that the secondary position has now started slowly to begin to make a bit of a white precipitate in there. So I think we've got a really clear order of rate of reaction here. Okay, so primary one is the slowest, the secondary one is the next slowest, and the tertiary one was the fastest. And in fact, we saw that starting to react before it even got into the hot water bath. Okay.